Hello, friends. In the next 15 to 20 minutes, we are going to cover a very important topic, that's physiology of fitness. I am Dr. Dipanjan Chatterjee. I have no conflict of interest and no disclosures. Why do we need to study physiology of fitness? Because extracorporeal support is life-saving, but it is dangerous too. And for proper utilization, all practitioners should understand the physiology of metabolism, oxygen delivery, and conductor removal. Only then we will be able to give optimal care. What is the goal of ECMO? It is to maintain adequate tissue perfusion with oxygenated blood. So, coming to the oxygen content of blood, and this equation we have all been studying since the first year of your medical curriculum. Oxygen is carried in blood in two forms, mainly by binding with hemoglobin and a very minuscule part by dissolving in plasma. And if we multiply this oxygen content with cardiac output, it will give us how much oxygen the tissues are getting per minute. So if we take a healthy person with a hemoglobin of 15, the oxygen content of blood, the arterial blood, which is coming out from the left ventricle, is approximately 20 ml per deciliter. Now, if we multiply that with our normal cardiac index of 3 liters per minute per meter square, the oxygen delivery comes to around 600 ml per minute per meter square. But our requirement of our tissues is only around 120 ml per minute per meter square. So the cardiovascular system is delivering 5 times our tissue oxygen need. The rest of the oxygen, which is coming out from the tissues into the venous blood, contains approximately around 16 ml per deciliter of oxygen and with a saturation of around 75 to 80%. The difference between the arterial and venous oxygen is only around 4 to 5 ml per deciliter. This blood goes to the right heart and right heart pumps the blood into the lungs where oxygen uptake takes place, which is also again equivalent to the how much oxygen has been removed by the tissue. So we see that our oxygen content in our arterial blood with a hemoglobin of 15 is approximately 20 ml per deciliter, and the oxygen content in venous blood is around 16. So 16 is quite a bit. The oxygen content in venous blood, which is rich in hemoglobin, is quite a bit, significant amount. So oxygen is being carried by binding to hemoglobin, minuscule part with plasma dissolved, and you compare that with carbon dioxide, where carbon dioxide is highly soluble in plasma and it is also converted to H2CO3 by carbonic anhydrase enzymes. So it is transported as a bicarb form. If we want to see what is the effect of hemoglobin on the oxygen content, you can see that the blood which is 100% saturated with oxygen, 100% saturation means that all the available hemoglobin is saturated, is bound to oxygen. As we come down on the hemoglobin level, the arterial blood oxygen content goes down. And we can see that the arterial blood oxygen content in the anemic patient is less than the venous content in patients with a normal hemoglobin level. So you can very well imagine that even the blood in the anemic patient may be bright red, but its oxygen content is very low. And hence, to carry oxygen to the tissues, we need adequate hemoglobin in blood. Usually, our tissue oxygen requirement is met by our oxygen delivery to the tissues because it is almost 5 times the delivery we compared to our tissue oxygen requirement. But if the tissue oxygen requirement remaining same and our delivery to the tissue goes down below the twice of the tissue oxygen requirement, there the metabolism becomes delivery dependent and anaerobic metabolism starts. It is precisely for this reason that we try to keep our oxygen delivery to extracorporeal circuit at least 3 times our tissue requirement. And if our oxygen extraction to the tissues is reduced, our venous saturation increases. If the tissue oxygen uptake increases, our venous saturation decreases. Coming to the oxygen carbon dioxide exchange in the membrane lung. So the membrane lung contains hollow fibers and blood passes outside the hollow fibers and gaseous gases are transported within the hollow fibers. So these hollow fibers they act as membrane against diffusion for oxygen and carbon dioxide from blood and the gaseous uh, substance. And the flow of oxygen and blood is kept in such a way and these fibers are bound in such a way so that there is a perpendicular motion of blood and gaseous flow so that there is adequate mixing of and all the blood can come into contact with the membrane surface. When we compare the alveolar surface, the gaseous exchange that is taking place in the alveoli, compare it with the membrane, you can see that the deoxygenated blood from the pulmonary artery comes through to the alveoli, the alveolar capillary, and there is a gaseous exchange taking place. The membrane of the between the alveoli and the blood, the RBC, is alveolar epithelium and the intravascular the capillary endothelium. So it is very thin, whereas if we compare it with the membrane lung, you can see that there is a quite a significant membrane thickness against which the gaseous exchange has to take place. So these RBCs which are passing across the alveolar capillary, they get saturated very soon. But the blood which is passing through the membrane, it takes time to get saturated because the gaseous exchange across the membrane is concentration dependent. Just across the membrane, there is a layer of RBC which gets saturated very soon. But as we go away from the membrane, the gradient of oxygen increases and less oxygen is reaching to the RBCs which is away from the membrane. For the carbon dioxide exchange, it is easier because carbon dioxide is very easily diffusible across these membranes. The membranes are set up in such a way that these barrier layer of RBCs they constantly change and more RBCs come in contact with the membrane. It is not a linear flow that is targeted within the membrane lung. Coming to the gaseous exchange, oxygenation depends upon the pump flow. How much is the blood which is passing through the pump? What is the oxygen which you are giving to the uh, membrane lung? How much is the hemoglobin concentration? How much is the venous saturation or the venous oxygen content? And what is the membrane surface area? So as more and more blood passes through the membrane lung, that blood will be getting saturated with oxygen. If we increase the oxygen concentration in the uh, our membrane lung sweet gas, like we are increasing the inspired oxygen concentration in ventilators, the oxygenation improves. Hemoglobin, since it is the main uh, carrier of oxygen, again, hemoglobin concentration, when it is going up, our oxygen content in blood naturally goes up. If the blood which is coming to the membrane lung is very deoxygenated, then the outlet blood will also not be fully saturated. And last but not the least, the membrane surface area. As we increase the membrane surface area, the more and more contact of blood and gaseous interface occurs and more gaseous exchange occurs. Compare it with the carbon dioxide removal. It is solely dependent on the sweet gas flow. So the oxygen content in our systemic blood, it will be dependent both on the oxygenation that is occurring across the membrane in the ECMO circuit, as well as what is the oxygenation that is occurring through when the blood is passing through the lungs. If the lungs are not functioning properly, then that fraction is reduced, and the soul of oxygenation is dependent on the solely on the membrane lung. But the net CO2 that is in the systemic blood, it is not exactly as the blood which is coming out from the oxygenator. Why? Because there is a mixing effect, as you can see in the next example. Suppose you have a venous return of 7 liters and a cardiac output of 7 liters, and your ECMO flow is 4 liters. So 4 liters of deoxygenated blood is coming to the ECMO circuit, getting fully saturated with oxygen, going back into the patient's right heart, and it is mixing with another 3 liters of venous return, because only 4 liters out of 7 liters of venous return was passing through the membrane blood. So this 4 liters of oxygenated blood with 3 liters of deoxygenated blood, they get mixed up. The net oxygen content depends upon the concentration of the oxygen in each part. So it is a admixture, venous admixture, which ultimately determines how much is the net oxygen content in the blood in the systemic circuit. Suppose the patient develops fever or sepsis, the cardiac output is going up. We have still kept the ECMO circuit flow as 4 liters, and the cardiac output has gone up to 10 liters. So the admixture will be 4 liters of oxygenated blood along with 6 liters of venous blood. So the net oxygen content in this blood will come down. So the CO2 exchange depends upon the sweet gas rate. It is not how much oxygen we are giving, it is a sweet gas rate. Like if the CO2 goes up in ABG, if the patient on ventilator, what you do is you increase the rate, increase the tidal volume. But here you have to just go up on the sweet gas rate. So flow meter will give us a sweet gas which controls the carbon dioxide, whereas this blender will give us a fraction of delivered oxygen and it will control the oxygenation of blood. One more important thing that determines the oxygenation that is admixture is the recirculation. That is, if you have the oxygenated blood returning to the right heart, a part of it is again sucked into the drainage cannula. Suppose you have a flow 4 liter ECMO flow, 4 liter of oxygenated blood is coming to the right heart, but the drainage cannula and the return cannula being closed together, part of the oxygenated blood is getting sucked into the ECMO circuit. So the net oxygenation reduces. Maybe the outcome of this is the output of blood from the ECMO circuit remains fully saturated, but you have a reduced oxygenation of the patient. In such a scenario, you have to increase the distance between the two limbs, that is the venous and the drainage and the return cannula distance should be increased. Another thing occurs in VA ECMO. What is it? That is, since we are returning blood back into the arterial system, the afterload increases. Though we are reducing the preload, the afterload increases, and because of the afterload increase, there is increase in the LV distension. And then this LV distension has to be judged and catered to as early as possible. Suppose you have put the patient on VA ECMO and this was the X-ray as the initiation. And after 6 hours, you see that the lung is getting flooded, the patient is in pulmonary edema. You have to think that the patient's LV distension is occurring and you have to vent the LV. You can see that the ejection has reduced, and these are the things that will give us clue that the LV is not contracting properly because of increased afterload. We have to increase the inotropy and reduce the load on the heart. Another important thing is that the ECMO pump flow is in the centrifugal pump is dependent on the preload and afterload. It's a non-pulsatile flow. Unlike the pulsatile flow of normal physiological heart, it is a non-pulsatile flow and it is dependent on the preload and afterload. Preload means the volume of blood in the patient. Suppose if the patient has sudden reduction in the blood volume, or the patient is passing increased amount of urine, or if the patient has an hemorrhage, then the ECMO flow will come down. We have to take care of the preload of patients who are on. And if there is any kink or if the afterload is high, if the patient is on high NORAD vasopressin support and you have put the patient on VA ECMO, the ECMO flow will be low. Need to know the pressure flow relationship within the tubing because resistance increases with the radius going down. Is the fourth power of radius, so inversely proportional to the radius. So more, if you want more flow, you have to increase the radius. Otherwise, your resistance to flow increases in the circuit. And you can see that the length of the circuit is also very important. As we increase the length, the resistance increases. So the venous cannulas, the drainage cannulas are usually long cannulas, and there is a they are the sizes of the venous cannulas have to be chosen properly to have a best flow for the patient. Finally, coming to the thirst reaction which occurs in the ECMO. So whether the ECMO increases or decreases the thirst reaction by helping to unload the ventricle, by increasing the tissue perfusion, by reducing the work done by the heart, by having a protective lung ventilation, all these reduces the inflammatory response. But there is also activation of inflammatory response in the circuit and in the membrane because it's an extracorporeal circuit. That will increase the systemic inflammation. So there is a balance between the increase and decrease in the tertiary aspect. Finally, the take-home message: the gaseous exchange in the membrane is dependent on the concentration gradient of gases across the membrane. The oxygen delivery is dependent on the blood flow uh, and the hemoglobin concentration. CO2 washout is dependent on the sweet gas, and the blood flow through the centrifugal pump is dependent on the preload and afterload. You need to be aware about recirculation in VV ECMO and be aware of LV distension in VV ECMO. If you want to go into further reading, there is a very good article by Bartlett. In this, you can go to the net and it is freely available. Please read it and you will be enriched with the knowledge. Thank you. Any questions? I am ready to answer.